Good morning. Welcome back. Judging by the larger number of students today, some of you probably think I'm going to talk about the exam. No, I got a request last night to postpone that until Wednesday, and upon reflection I realized it was the better choice. So you're stuck here listening to new material. I'm sorry. I apologize. I don't really apologize. I thought I would send out an announcement, and I said, nah, let them come to class. Yeah, I think it's wrong to miss class. Wrong, not in a moral sense. I think it's misguided. I do think you get more from coming to class than from watching a lecture online. And there are several reasons for that. One is, it's a very good forcing function. And we all need forcing functions. If you know that you can watch it later, you know you can watch it later, and then you don't watch it until you get near the exam time, and that's a terrible time to study. Really terrible. I know from my own experience, they started recording the distinguished lecture talks, and I'm always busy, so I always struggle when the distinguished lecture comes around. It's great, but I don't have time. Well, it's recorded. And there's a library, and I can watch it anytime. Do you know how many of them I've watched in the last 3 years? 0. Yeah. That's one reason. The second reason is that I think you learn better when you are engaged with someone socially, face to face. I think there's a lot of evidence for that, but I kind of also feel it in my gut from my own experience as a learner and from teaching students over many, many years. You know, you think that the videotape is great. You can stop it at any time, get coffee, come back, watch it while you're doing something else. It's true, but it tremendously reduces the quality of your engagement. Learning is a very emotional process. You think it's just cognitive. You think it's just, you know, they're just showing you some logic thing and you either memorize it or understand it. But no, it's a very emotional thing. You learn better when you care. You learn better when you're in a social setting. So even if you don't participate, which is another bad idea, always try to participate. But even if you don't participate, you're much better off sitting in class than watching it on tape. That's what I think. Okay, so let's talk about neural networks. Neural networks are very big today in machine learning. They were very big in the 80s, and then they stopped being big for a while, and now they're big again. And I don't mean to say it in a mocking way. I think there are very good reasons for them to be important then and for them to be important now. So I'll tell you a little bit about the background of where they came from, and then where, you know, what we really see them as now. It's not the same thing. So they came from brains, right? I mean, the inspiration for neural networks comes from people's brains and animals' brains. We look at brains and we marvel at what they can do. And then we try to look inside and figure out how they do it. And as far as we can tell, the way they do it is extremely different than the way we do things with computers today. So there's the brain architecture, which is a large number of very simple things called neurons. We think they're simple, very simple computing elements, interconnected pretty heavily. And then there's the modern computer architecture, also known as the von Neumann architecture. In a von Neumann architecture, you have a CPU where all the computation is done, and you have a large amount of memory. And the CPU gets instructions, and it figures out, oh, I need to get this from memory and this from memory, and add them together, and then store that in memory. So all the computation is centralized in one processor, or 8 or 16, but in a small number of processors. And the rest of the apparatus, the vast majority of the apparatus, is passive memory. Passive storage, rather. I don't want to call it memory. That's kind of anthropomorphic. Passive storage. Very, very different architecture. And starting in the 40s, brain researchers, who was no computers around, barely, were thinking of the brain as a computing device. Interesting, if you look at the history of how people understood the brain in the last 150 years, you will find that at any generation, the the best metaphor, or the way people understood the brain, is based on the most complicated technology of the time. So the most advanced and complicated technology of the late 1800s was the steam engine, right? The Industrial Revolution and steamboats and steam trains, right? So how did Freud think about the brain? You know, all these pressures building up, and the need to release a valve, and right? That was the metaphor of the brain, of all these internal chambers building up pressure. What was the big complicated system of the 1930s? Telephone networks. They were all over the world, and they resembled the brain with all the wires and stuff. So a lot of discussion on understanding brain was in terms of communication, this big communication system. Of course, what communicates with what was left unanswered. And then in the 50s, we got computers, and then the brains became computers. Turing's hypothesis says that it's going to stop here, that it doesn't go any further than that. The Church-Turing hypothesis says that computers are as complicated as things can be, or as powerful as things can be. But understanding the brain as doing computations started around that time. And it became very clear in the 70s that they're doing it very differently than people. So there was than computers. So people started thinking, okay, maybe there's something about this kind of parallel computation that is capable of doing things that we can't do with the von Neumann architecture. And many people still think that today. Of course, you can simulate anything with the von Neumann architecture. So it's not that if you use a von Neumann architecture, namely a regular computer or PC, you can't do these things in principle. But it's not natural to think about them that way, and it may not be efficient to think about it that way. So it's not a question of computability. You can simulate supposedly anything with anything that's Turing equivalent. But it's a question of, is this the right level at which to think of solving problems? Should we think about them, the kind of problems that we try to solve in AI, should we think about them as algorithms, the way we're used to programming an algorithm, like to do a sort? Or should we think about them the way they seem to be implemented in our brain, which is a very massively parallel combination of very simple computations? All right, so that's as far as historical introduction. What do the brains look like? I assume most of you know, but let me draw it. This is a neuron. It's got a little thing inside that's the nucleus, but this is a neuron. It's a cell. It doesn't look like this, really. The shapes of neurons, these are neural cells in our brains, are highly diverse. They have many, many shapes. Sometimes they're extremely long. Sometimes they're branching out. Sometimes they're triangular. They have all kinds of shapes. And of course, they're three-dimensional. But the important thing is that it has many inputs. In fact, it starts with like one input, but then it branches out. It might even have many of them. Many, many inputs that conduct electrical signals from other neurons. I will skip over the details. It's just to say that it's not strictly electrical. It's an electrochemical connection. There's a switch between electrical signal and a chemical signal. And then there's an output. And the output is in the same shape. There's electric voltage in the neuron, and this voltage is changed by the inputs that come from other neurons, typically is being brought up. And this functions a little bit like a step function in the sense that it accumulates this voltage, and it doesn't do anything with it until the voltage rises above a certain threshold, and then it shoots out a pulse of electrical current and goes back to a low voltage level. So it accumulates stuff and then shoots and goes back, and then accumulate more stuff and then shoots and goes back. And all that is happening pretty fast. How fast does it happen? Well, if you stimulate a neuron with a lot of electrical current, as much as you need, as much as possible, it can fire as fast as 1,000 times a second. That's very fast, 1,000 times a second, okay? maximum firing rate is 1,000 seconds. Of course, I'm saying it a little facetiously. 1,000 times a second is very fast for us, but it's not very fast for computers, for our modern computers. But this is the time step at which brains work. If you believe that the way they process information is by firing those shots, which is what we mostly believe. Now, 1,000 firings a second is not much, but they have to ask us of how many neurons do we have. Does anybody know the answer? 10 to the 10, 11, 10 to the 11 neurons. These are called synapses. Every time one neuron is connected to another, it is connected through something called a synapse. It's the electrochemical interface. How many synapses do we have? Nobody knows? 10 to the 15. These are the connections. So this gives us about 10 to the 4 connections per neuron, average. Of course, there are great variations, like in everything in biological systems. But keep these numbers in mind, so to speak, haha. They're important. She got it. It's important to know the branch-in factor here. And the average branch-in factor is also the average branch-out factor, right? So, if so many connections come in here on average, then so many connections should go out on average, not necessarily for every neuron, but on average. And this happens when this axon splits and connects to many other neurons. So every neuron is connected to an average, an order of 10,000 other neurons that give it input and produces output on average to 10,000 other neurons. It's an interesting number. It's not quite, but it's almost the square root of this. So you're connected not quite to the square root, but square root would be 10 to the 5.5. That's 10 to the 4. It's a large fraction. Well, it's a small fraction, right? It's 1 in 10 to the 7, but it's a sizable fraction. What else do you need to know about real neurons? These connections can be either excitatory or inhibitory. Let me write this. Or inhibitory. An excitatory connection means that as the neuron sends a message, it increases the voltage of the neuron it's connected to and therefore makes it more likely to fire. An inhibitory connection does exactly the opposite. It inhibits that neuron from firing. Okay? In real biological systems, these excitatory or inhibitory connections depend on the type of neuron that it is. In the artificial neural networks that we're going to deal with, we blur over this distinction and we allow any connection to be either excitatory or inhibitory. Does that make a difference? Maybe. I don't know. All right, so here comes the most interesting story. You take a bunch of people, like you, like me, you sit them in a dark room. You put a little red button in front of each one of them. You start showing pictures on the screen, just like here, one after the other. You instruct people to put their finger on the button, and as soon as they see a picture of their grandmother, they need to press the button as quickly as possible. You show them lots of pictures, including some pictures of the grandmother. They push the button. You measure very carefully how long it took them from the moment the picture showed on the screen until the button was pushed. And the answer, very roughly for most people, is 0.1 second. Have you ever tried to do something in 0.1 second? Like, I try to click my watch twice as quickly as I can, and when it's the stopwatch. If you're really good at it, you can get down to about 0.1 second. This is the grammar recognition time. Now let's translate this into neurons. What neurons had to fire? Well, the picture getting into your retina is instantaneous. It's the speed of light. But from your retina, it travels to the back of your head, to the visual cortex. It goes through V1, the first layer, V2, and then goes on into other layers. And you extract features from it. You extract color, lines, orientations, shapes. At some point, you access your stored memory of grandma. And at some point, you do a match. And the match, think about grandma in the picture. She could be big, she could be small, just like the puppy, right? She could be partially occluded. She could be when she was young, when she was older. She could be wearing glasses. She could be wearing a hat, you know, all kinds of grandma positions. And you have to deal with all of that and recognize, yeah, that's her. And then once you recognize that, you have to be cognizant of the fact that you have a task to push the button. And there's some decision mechanism in your brain that makes that decision, yes, I have to press the button. And that translates into movements of muscles in your hand, or into neurons that shoot down messages through your hand and press the button. Okay? That's a complicated process. But especially the part about recognizing if it's your grandma or not, once you processed it. What is the longest chain of neural firings that happened in this process? Well, put these two numbers together. Maximal firing rate is 1,000 firings a second. You did this task in 0.1 seconds. That means the largest chain was 100 firings. So 100 neural steps. A 100 sequential steps. Your next assignment is to write a program that can run on as many computers as you want that would recognize a grandma from an image in 100 parallel steps. Wake me up when you're done. We don't know how to do that. Actually, with deep learning today, maybe we do. We didn't used to know how to do that until we didn't used to think that it was possible until our brains show us an existence example that is possible. So it's quite remarkable that you can do all this kind of processing, that something can do all this kind of processing in 100 time steps. So this is the source of inspiration of neural networks, that they were doing things that we didn't think were even possible, and we certainly did not think were possible with the von Neumann architecture. So trying to benefit from that and trying to understand how the brain works were kind of done together in the 70s and 80s, but it wasn't getting very far. I mean, people who were working on understanding the brain were making progress, and they continue to make progress. But benefiting from it was not working that well as a way of doing the things that people do, but sort of getting our artificial neural networks to do the things that brains do effortlessly. But what was working well is we've discovered that these networks are very nice general regression tools. They're a very nice step above linear regression. So for a long time, this is what we used them for. They were just, think about a linear regression, but no longer restricted to be linear, which is actually kind of nice. A very general way of learning functions in a regression setting. So we're going to talk about neural networks in that context and see how successful they were there as sort of generic regressors, generic nonlinear regressors, and then catch up to the last 10 years where some more interesting progress was made. All right, so we're going to switch now from talking about real neurons to talk about artificial neurons and artificial neural networks. And then, all right, so this is going to be our artificial neural network, an artificial neuron. It's going to be characterized by having many inputs. These are inputs. And possibly many outputs. It's going to hold a single number. So it's a very simple computing device. It just holds a single number. It could be a continuous number. The inputs are all assumed continuous. That is not a real restriction. If you want to input something that is binary, the binary is a special case of continuous. If you want to input something that's an integer, that's a special case of continuous. So we'll think about it in general as continuous input. And there would be n of them, or I'll call it p of them, because I like to use p for the number of covariates. And we'll think typically of one or more continuous outputs. We will worry mostly about a single output, so I'm going to write it a little bit differently. I will assume that there is a single output that comes out, and then later it could split and connect into many, many neurons. But it's the same output connecting to all of them. Here are the inputs. Call them x1 through xp. And the rule for the output is relatively simple. You generate the output in a two-step process. The first step is to linearly combine the inputs. The second step is to take the combination, the linear combination, and pass it through some transfer function. So let's talk about them one at a time. Step one. Linearly combine the inputs. So this means that the net going in is just a sum of some weighted combination of the xi's. I goes from 1 to p. Now, by linearly combining, we mean weighted linear combination, and the weights are associated with the connections. So we will put w's here for weights, w1, w2, all the way to wp. W's are also real, wj. The weights could be positive or negative, corresponding to excitatory influence or inhibitory influence. And it could, of course, be 0, corresponding to no influence. So here we have wi, xi. Now, written this way, the kind of function that's implemented here is the function we're all familiar with, the linear transformation of the inputs into a single output. And it has the property that 0 inputs will always translate into 0 output. We want to enrich the space to make it truly affine transformation. That means linear plus a possible offset. There are two ways in which we think about it. One is to introduce a certain, well, let me just do it one way. Let me do it the same way I did it in linear regression. Add a pseudo unit here, a fake unit, call it x0 and make it equal to 1, and then add a weight of w0 here. Just like we did with linear regression. I'm adding a fake covariate so that it's as if I added a w0 here, or I can just write it as summation I goes from 0 to p, wi pi xi, or I can just write it as w dot x. Many ways of writing the same thing. So the first step is very familiar to us, just linear transformation. Second step, a transfer function. That means that the output equals to this transfer function, which I'll write like this, of the net. So the full function is written as the transfer function applied to w dot x. What is this transfer function? Well, it could be anything you want. If you try to get inspiration from the brain, it looks like a very nonlinear kind of thing, because I mentioned that a neuron gets lots of stimulation and doesn't do anything, and then all of a sudden it gets sick and tired and shoots something, and then goes back to sleep. So that's a classic nonlinear kind of behavior. You could have different transfer functions for different neurons in the network, right? Or you can have them all being the same transfer function. So this is your artificial neuron, and then we can combine neurons into networks. That means every one of these guys can sit in any kind of combination, and anything can be connected to anything. In other words, you have a directed graph. Directed because the links are the direction of firing, and you can even have one neuron firing into another and then one firing back. In fact, in the human brain, you get a lot of connections like that. They're not always, sometimes they are direct to neurons, sometimes there are much longer cycles where you have a whole bunch of neurons connected to a whole bunch of neurons, connected to a whole bunch of other neurons, and connected back. In fact, it's a general rule in the brain that you almost always have back connections. Very hard to analyze a connected network like that, a cyclic network like that. We're going to restrict ourselves to considering only directed nets. In a directed graph, you can impose an order of the nodes such that no node higher in the hierarchy, no node lower in the ordering is connected to a node higher in the ordering. Okay, so you can scan, you can process all the nodes in the order of firing. So a directed graph basically means a directed acyclic graph, I should add. Well, let's start with the directed graph. We will restrict ourselves to directed graphs, and then the further restriction would be to a directed acyclic graph. A DAG. Do we want to restrict ourselves to a DAG? No, just directed graph. Forget that. We're also going to spend most of our time talking about layered neural networks. Layered artificial neural network. In the layered neural network, you start with your inputs. Then you have a layer of neurons here of any length, of any size. It could be smaller than the number of inputs or larger than the number of inputs. And each one of the neurons here would be connected to some subset or all of the inputs. So it would look something like this. You can have as much as a full connection or just partial connection. This is called the first hidden layer. It is not really hidden. I'll tell you in a minute why we use the term hidden layer. It's not hidden. You can look at it. You can talk to it. And then the neurons from this layer are connected to the next layer, which again could be smaller in terms of number of neurons or larger or the same as this layer. And this process can repeat as many times as you wish. This would be the second hidden layer. Until you get to the output layer. And the output layer could have one or more outputs. One output if your goal is to calculate a function of many numbers into a single number, or more than one output if your output is something more complicated than that. William?
What does it mean to restrict ourselves to directed graphs? What kind of graphs will go that likely have?
Not directed graphs. What I meant is not cyclical graphs. Thank you. They're all directed because all the connections between neurons have the side acyclical. And the kind of graphs that are ruled by acyclical graphs are cyclical graphs. Yes?
Sorry, it's
Thank you.
like a question for clarification. You just said that furthermore we want to restrict ourselves to DAGs, but I think DAGs are not acyclical.
DAGs are not acyclical. The A in DAG stands for acyclical.
Oh, really?
Directed acyclical graph, yeah. Okay. Sorry, my bad here. The point is, our brains are full of cyclical networks. And there is tremendous power in a cyclical architecture because the calculation is not a one pass. It could be even a very long computation that passes through the network multiple times, and every time it does something different. So there are specific functions that might be easy to do in a cyclical network and not in a acyclical network. We're going to restrict ourselves to the kind of functions can be implemented with an acyclical, one pass to the network. Let me go back to my layers. There's multiple layers here, and then there's output. And the output could be a single neuron, or it could be more. For simplicity, let's assume now that it's a single neuron. Each one of the lines I drew has a weight associated with it. So there's a tremendous number of weights in this network. Many more weights typically than neurons. Furthermore, each one of these neurons, in addition to all the weights leading into it, has this W0 weight that is connected to the fake or pseudo input 1. So it's this guy. Every neuron has its own W0. The W0 you can think of as a bias in the sense of changing or a threshold or a offset. You can call it any name. It's not the same as inductive bias, and it's not the same as statistical bias, but it's called bias. It can shift the answer. So the number of weights overall here is very large, and then out comes a number. Question?
Do you have a W0 in the second hidden layer?
Yes, you have W0 in the second hidden layer, and in every layer. There's a W0 here, W0 here. You can assume that there's one big X0 equals 1 here, and everybody's connected to it. Or you can just forget about this guy and say there's just a W0. It comes out of nowhere. Yes, you don't have to, but you typically allow for a bias into every neuron. So what I described now is a computing device in the following sense, that once you fix the topology of the network, that means how many neurons there are and how they are connected to each other. Then you fix the weights of the network. Each weight is a continuous number, positive, negative, or 0. And you fix the transfer function. Once you fix all three, you've now fixed the function that the network is computing. And that function is simply, for any input, you plug its values in here. You go to the first layer, calculate the weighted linear sum of the inputs into it, including the W0, the bias. Take the output, pass it through the transfer function, and this produces an output out of here. And this output gets replicated into all the neurons that this neuron is connected to. You repeat that for all the neurons in the first hidden layer. When you're done, you repeat that for all the neurons in the second hidden layer. And you keep propagating forward until you get all the inputs into this layer, into this unit. You do the same thing here, and you get out a number. That sounds like a lot of computation, but it's a very straightforward computation. It's called a feedforward computation because you feed the signal forward through the network. So these kind of networks are known as feedforward networks. Now, you may not be able to write down what this function is. What is this implementing? So you don't have an analytical description of the function, but you have the function in your hand. You can feed in an input and see what the output is. What happens if you change some of these things? What happens if you change some of the weights? You change the function, right? What happens if you change the transfer function for one or more of the units? You changed the function. And of course, if you change the topology, you're definitely changing the function. You have a different number of, potentially different number of weights. So this is not, well, there's no learning here, by the way, so far. No learning whatsoever. All I'm describing is an apparatus, a machinery for representing a function. Just like a decision tree is a machinery for representing a function. Big difference between decision tree and neural networks is decision trees usually represent classifications, although they could be used for regression, but we talked about them as classifiers. Neural networks is exactly the opposite. They're naturally designed for regression, although, of course, you can take them and treat them as if they're doing classification. For example, you can decide that if the thing that comes out at the top is greater than some value, the answer is one way, and if it's less, the answer is another way, so you have a binary classifier. So you can always take a continuous output and somehow interpret it as a binary classification. But by and large, neural networks are used for regression, for producing numbers, either single numbers or larger number together. Yeah?
What is the advantage of having layers?
What is the advantage of having layers? We will talk about it a lot. Let me give you just a hint. I mentioned that if you change the topology, the answer changes, right? What do I want to say at this stage? Let me just say it changes the kind of functions that can be expressed. Hard bias. But not only. Not only. Also change learnability. All right, so we're going to move back to machine learning mode of thinking, and that means I'm going to pose my famous 3 questions. My famous 3 questions are hard bias, soft bias, and search. And we're going to try to answer these questions as a function of these things. Topology, transfer function, and weights. So far I described a fixed point, a fixed topology, a fixed weights, and fixed transfer function implement a single function, right? Now, let's say we fix the topology, and we fix the transfer function. We allow the weights to change. As we allow the weights to change, the function that's implemented changes. Now we can ask ourselves, can we find a combination of weights that implements the function we want? So we define a space of functions that are expressible in this particular topology with this particular transfer function. So we can ask the question, is there a hard bias? Namely, are there functions that cannot be expressed this way? And if there are, which functions can be expressed this way and which functions cannot? And then the next question we're going to ask after that is, among all those that can be expressed this way, which ones would we prefer? And then the last question is the computational one. How do we go about searching that space? It's basically searching the space of weights. So we're going to start with the simplest possible network, which is a single unit, and with the simplest possible transfer function, which is the transfer function that doesn't do anything. So the transfer function that takes the net and produces out the net, namely doesn't do anything. In other words, it takes the w dot x and produces w dot x. It's the identity function. If we draw it here, this would be our net, the result of the linear combination of the inputs, and this would be sigma of the net. This function would look simply like this, 45-degree angle. Right? That's the y equals x line. This kind of a neuron is called the linear unit. And basically what it does is it does a weighted average of the inputs and produces that as the output. This should be familiar to you. What does it look like? It's linear regression. There's no difference. It's exactly linear regression. The expressive power is the same expressive power of linear regression, which is all linear functions of the input. Kind of trivial, right? So we'll put it here. One linear unit. And I will put here that little picture of the transfer function. And the answer to the hard bias is all linear functions. How do we, what should we use as our soft bias? We could use anything we want. It's our decision. It depends on the domain. But a very commonly used soft bias is looking at the error that a network makes on our training data and trying to minimize the sum of squared of errors. Okay? I already mentioned to you that this is somewhat akin to assuming that the errors come from a Gaussian process. Call it mean squared error. How do we define error? We sum over all our training examples, which I'll call D. D goes from 1 to n. And we look at the difference between the correct output and the correct value, the label, and the actual output produced by the network, which I will call, I'll call this the teacher or the truth and this is the output. So D is the index for the number, the training example, and T stands for truth, or for target, or for teacher, or for label, spelled with a T. And O stands for output, the actual output of the network. This is how we defined sum squared errors, or if you divide by n, mean squared error. Now my question to you is, what is this a function of? What are we going to be optimizing? The weights. Where are the weights? I don't see weights here anywhere. Are they here? No. Are they here? Yes, the weights are hiding in here. So let me make that explicit. I'll put a big bar here for these are the vector of all the weights in the system. And I'll make it explicit here, that this is a function of the weights. At this point, I fixed the topology and I fixed the transfer function. So this is strictly a function of the weights. Now my search can be thought of as a search in the space of the weights. How many weights are there? In this particular case, since it's a single neuron, if there are p inputs, there are p plus 1 weights. Just like the betas in linear regression. Same thing. So, if I ask the question, how do I do a search to minimize the mean squared error? What do you think? How would you search to minimize the mean squared error? I'm looking for the weights, so what I'm going to do here is say the winning weights are the ones that minimize over all possible weight vectors the error function, which is a function of the weights and the training data. Yes, you were going to suggest, how do I do the search? Yeah?
Isn't this OLS?
Yes, it is exactly OLS. Thank you. We don't have to do a search. We can solve it analytically. Thank you. Thank you. I hope the rest of you thought it was so obvious that you didn't bother raising your hand. Yes, we don't have to do a search. We can just do OLS. But I'm going to do a search anyway, just as practice for when OLS will not work. But let me write here that, yeah, OLS formula. Or I'm going to do a search called gradient descent. So to explain what gradient descent is, I'll tell you another story. You are parachuting in the night into an open space in a large, very outdoorsy kind of hills and valleys and natural area, and you're parachuting with a bunch of your friends, and it's pitch dark, and you agreed you're going to meet somewhere, and since you don't know the terrain very well, you agreed you're going to meet at the lowest place. Okay? Lowest place. Just find your way to the lowest place. You all parachute. You fell, I don't know, various distances from one another, and now you're all alone. It's really dark, you can't see anything, and you have to find the lowest place. What do? Well, you can't see anything more than a foot away from you, but you can feel the land with your feet. So one thing you could do is kind of feel all the way around you until you figure out the direction in which the land is sloping down the most. And then you take a couple steps in that direction, and then you stop, and then you feel the land around you again, until you find the direction of steepest descent, steepest drop, and you take another step, and you keep doing that. That's what gradient descent is. You look at the lay of the land right around you, the slope of the point you're standing on. You find in which direction that slope is the steepest. You take a step, and you take a few steps, and then you do it again and again and again until what happens? Until you get to the place where anywhere you look around you, it's up. There's no more down. You've reached the minimum, and you expect all your friends to be there, right? Yes? No? Why not? Because there may be multiple minima. So that's not a very good way to meet your friends. Depending, of course, on the lay of the land. If the land is fairly easy flowing, it's not full of bumps, and everybody landed within one basin of attraction, then you will meet. But if it's got multiple, valleys and stuff, then you may not meet. That's the story of gradient descent. So I want to show you a picture from Mitchell's book. Before I do, let me just give you the math for it. Gradient descent in the space of errors means that you calculate the gradient, which is basically the derivative of the error with regard to each one of the weights, and you take a step in the direction of steepest descent. In calculus notation, we would say the derivative with regard to the weights of the error function, which is a function of the weights, is the direction and the magnitude of the step that you will take. The derivatives in calculus are usually written such that the positive means it's going up. But you want to go down, since you're trying to look for minimum error, so you would introduce a negative sign. And also, you want to take very small steps, so you may introduce a multiplier here called the step size. Forget what this letter is called. Eta, maybe. This tells you how you should change your weights. So your new weights, what it would be. Oh, he only shows you the delta. That's fine. So the delta in the weights is defined, the change in the weights from side to side is defined as the negative constant, small constant, times the gradient. Or, if you're unhappy with vector calculus, we can write it in terms of partial derivatives. The change in weight for weight I is negative eta partial derivative of the error with regard to weight I. This is exactly the same thing. This is just vector notation. This is the definition of gradient descent. Let me show you the beautiful picture. I think I mentioned to you that the reason linear regression can be solved so easily is because it's a convex problem. And because here we're talking really about linear regression, we have a convex problem as well. The picture that you're seeing is the error surface. Error surface is the function that expresses the value of the error function as a function of all the weights. Because we're restricted to 3 dimensions, the example here is of only 2 weights. Okay? But in any real-world network, including one that has a single neuron, you would typically have many more than 2 weights. So this is really an extremely, extremely simplified case. But the 2 weights are called here W0 and W1, and they go along the bottom, X and Y, and then the Z is the error as a function of the weight. And the picture that you see is the quintessential picture of a convex function. It is smooth, it doesn't have any bumps in it, and it's got a single minimum. When you apply gradient descent to a convex function, you will find the global minimum. So this is one way in which we can do this. We don't have to. We can use the OLS, maybe faster. But it gives us an opportunity to see what happens with gradient descent when you have a convex error function. It doesn't matter where you start. In this example, you start in this place with this vertical line. Following the gradient, you will end up at the lowest place. You can start from many different places. You will always end up in the same place. The one caveat is the step size. If the step size you take is too large, you may be skipping over the minimum and then turning around and skipping over back forever, right? You may miss the actual minimum. In fact, that's true for any finite step size. But it's a real problem if your step size is too large. What if your step size is too small? It'll take a lot more computation. You'll need to repeat the computation many more times. But in general, gradient descent is a perfect solution for convex functions. What else did I want to show you? Here's how we derive the gradient descent algorithm for this very simple case of a linear unit. Remember that the error is defined as the sum of squared differences between the teacher signal and the output, the T sub D minus O sub D. You may wonder what this half is doing there. It doesn't have to be there, but for convenience, we define the error as half times. So I had the error defined there, but let me try to use my cursor here. Can you see it? Yeah. This half is a constant. It doesn't matter. For the purpose of minimizing an error function, you can put any constant here. And the reason we put it here is because we know it will be handy for simplifying the expression later. So we move the partial derivative operator inside the summation. Then we take the partial derivative of this quadratic term. So it becomes 2 times the original term times the partial derivative inside here. Remember, this 2 will cancel with a half. Remember that T is a constant. This is the teacher signal or the label. The actual dependence on the weight is here. And what is the dependence on the weight? Remember, the transfer function is nothing. It's the identity. The output is simply the dot product of the weights and the inputs. And the derivative of this dot product with regard to weight Wi is simply x sub I. So you put all of this together, and you have this formula. You should go over this at home just to kind of practice your derivative skill. But the important thing is that whenever you are asked to do gradient descent, you start with something like this. You start with delta E to delta Wi. And then you go through the calculus steps. And this gives you an update rule. All right, I'll stop it here. All right, so our solution here to the search problem is either OLS or gradient descent. You know, it doesn't get any more perfect than that. We have a complete search solution. We have a very simple soft bias. The only problem is we can only solve linear problems. And if all we wanted is to solve linear problems, we didn't have to start with neural networks. We can stay with linear regression, which is really what this is. But this is a single neuron. So maybe we can get more power by considering a whole network of linear units. Okay, so that's going to be the next apparatus we're going to consider. Not one linear unit, but a network of linear units. If you remember the three things we have control over, topology, weights, and transfer function. We're still keeping the transfer function linear, right? Or not doing anything. But we're now allowing the topology to be anything you want, and the weights to be anything you want. So now let me ask the question again. What is the hard bias of a network of linear units? What kind of functions can you express with it? If you're allowed to configure it with as many units as you want, connected any way you want, and any weights you want, what kind of things can it calculate? What kind of things can it not calculate? What kind of functions can be expressed or cannot be expressed? Can you express any function? You can have as many units as you want, as many layers as you want. Yeah?
I would say yes.
Yes, you can express anything.
For example, for each, you could just create a neuron for each possible input and assign it a weight from the beginning. And so yeah, with enough neurons, you could basically program it.
So with enough neurons, there will be no hard bias. Is that what you're saying? Okay. Anybody wants to agree or disagree?
Not any.
Not
I
any.
would not say that, because don't forget that for each neuron, it's a linear combination of the input.
Right.
So this is a hard bias that will never change. So as long, so though you have many like infinite neurons, but there's always a hard bias on a single neuron. So
On a single neuron, but I'm asking, you're saying there's always a hard bias on a single neuron. That is true. I'm asking, what is the bias of the network as a whole? What kind of functions can the network not represent, or can it represent any function? Go ahead.
I think the network can represent, with one linear unit, you can represent an or X or so I think that the network can represent a combination of representing function.
One linear unit can represent XOR? I don't think that's true. Linear unit can... How would you do that? Okay, no, you cannot represent XOR with a single unit. Second, please.
Would it be able to represent all polynomials?
Will we be able to represent all polynomials? What is your thinking? Why?
Because it's sort of like you can compose linear functions, and if you plug them linear, you can have linear.
Okay, so it's more of an intuitive reasoning that that neurons compose functions from the inputs from the neurons that they feed into them. So you're thinking that would result in polynomial functions. Interesting. Okay. Other questions? Other answers? Please.
If that's true,
Yeah.
if a linear combination can represent all polynomial functions, but according to a polynomial approximation theorem, we can represent all infinitely differentiable functions as well.
So you're saying that if it's true that you can represent any polynomial of any degree, then you should be able to present any function to arbitrary approximation, because polynomials are dense. They are. Yeah. Okay.
If it's infinitely differentiable.
Yeah. Okay. True. William?
One upper bound that we can get is clearly any function that's represented by such a network is continuous, so you can't represent it as continuous function.
One upper bound, one hard bias, is that the function you represent must be continuous, because each one of the neurons implements a continuous function. Linear functions are continuous, and a combination of them is also continuous. I would tend to agree with that. Okay, well, that's a big bound. Most functions are not continuous, but most functions we're interested in are continuous. Yes?
Even a linear combination of linear functions.
Thank you. Thank you. So, yes. This maybe surprising answer is that the hard bias of a network of linear units is the same as the hard bias of a single linear unit. Namely, it can only represent linear functions because, so your intuition, I think, was in the right direction, but the conclusion is a little different. A linear combination of linear functions is also a linear function. And the linear combination of linear combinations of linear combinations of linear functions is also a linear function. Linear functions are closed under composition. Let me first write it and then try to convince you. Still, all linear functions. We didn't gain any expressive power. We didn't change the hard bias. And if we were unhappy with the hard bias, adding more linear units is not going to change that. How do I convince you that this is the case? Let's take just two hidden units. Here are the inputs. Let's say they're all connected this way, and they're also all connected the other way. Let's assume that all these weights are called W1 through WP, and these weights are called G1 through GP, or V, let's say V1 through VP. Now you have these weights that are U1 and U2 and U0. And here comes the output. So the output is sum, I won't bother with the indices, of U I times the output of these. So this is the output of unit 3, and this is the output of unit 1, and this is the output of unit 2. So this is output I. All right, I'll bother with the indices. This goes from 0 to 2. Okay, the total output, output 3, is a weighted sum of the input from these. But these themselves are weighted combinations. That would be, the first one would be sum of the Wi xi, well, j. And the second one would be the sum of the, these were w's, these were v's, vj xj. If you open the parentheses, this is a constant, these are constants, these are constants. You open the parentheses, you rearrange everything, you're going to get a linear combination of the x's. And it doesn't matter how many units you have here, and it doesn't matter how many layers you have, it's all linear. Let's not bother. If it's not going to change our hard bias, and everything else would remain this, and we already have a perfect solution here, we have two perfect solutions, then there's no need to consider this anymore. The problem is that we cannot leave the world of linear unless we do something drastic. If we want to try to learn more interesting problems, more interesting functions, we have to step out of linearity. Good word, step out. Didn't think about it. So we're going to go into a nonlinear function called the step function. Step transfer function. Here's the net. Here's the output. The linear functions look like a straight line here. The step function would look like this. Oops, sorry. Very nonlinear, only in one point. but it's still nonlinear, right? It's 0 everywhere here, and then it becomes 1 all of a sudden. Step function. Why do we use it? Because it's very simple, and it's inspired by the brain. I mentioned to you that the brain behaves as if nothing happens, or any particular neuron gets stimulated and doesn't respond, and all of a sudden it fires and goes back. This looks like a step function. These step functions have been studied very heavily in the 60s. They got the very unfortunate name perceptron. Perceptrons. Very unfortunate because when they were invented, people thought, or when they were studied, rather, people thought they were the answer to how the brain works, and the brain does perception. So these are the basic units of perception, so they're perceptrons. But that's a mistake that AI people make all the time. They give their models names, very inspiring names, like that imply understanding, like deep understanding or something like that. And then people confuse the model with the reality because of the name. So be it as it may, these are perceptrons. And we're going to start by studying what a single perceptron can do. One perceptron. And I will remind you that the transfer function looks like this. The one thing to notice about perceptrons is that their output is no longer continuous. Linear units and networks of linear units have continuous outputs. So the space of functions that they can represent are some subset of continuous output functions. But perceptrons all of a sudden became classifiers, binary classifiers. They have two outputs, 0 and 1. Okay, but we can still ask ourselves what hard bias do they have relative to other binary classifiers. So what kind of binary classifications can they do, and what kind they cannot do? So what kind of binary classification can a single perceptron do? Yeah? Can do an AND. Well, you're assuming that the inputs are discrete as well, right? Yeah, but the inputs could be continuous. But yeah, they can do an AND. What can they not do? Yep.
They have to be like feedforward, right?
No, I'm talking about a single. You're talking about feedforward. I'm talking about a single perceptron. What kind of functions cannot be? What kind of classifiers cannot be implemented with a single perceptron?
Like anything that's linear.
Anything that's?
Like not like this shape, like anything like linear polynomials.
Well, this shape applies to the transfer part. But I'm still thinking of the perceptron as something that here's the transfer part. Here are the inputs from x1 to xp. Here are the weights. Here's another weight, w0 from 1. The perceptron does a linearly weighted summation of its inputs plus the bias term, and then passes it through this threshold and produces out either a 0 or a 1. Perceptron is very much like a linear unit. Most of the computation it does is in the weighted summation of the weights. The only difference is, instead of passing out the weighted sum, it passes out a yes or a no. Is it above a threshold or not? So a linear unit can only represent linear functions. A perceptron can only represent linear distinctions, linear separating surfaces, linearly separable problems. What are linearly separable problems? These are problems that you can separate with a linear hyperplane. So in 2 dimensions, if you have data in 2 dimensions and it looks like this, these are the positive examples, these are the negative examples, we would say that it's a linearly separable problem because you can separate it with a straight line in between. If you have data in 3 dimensions, it is linearly separable if you can pass a plane that puts all the positive examples on one side and all the negative examples on the other side. In higher dimensions, a problem in d dimensions is linearly separable if there exists a d-1 hyperplane that separates the positive from the negative examples. The answer here is all linearly separable classifications. You may think we didn't make much progress because we're still linear. That's true. But when we take the next step of building a network of perceptrons, all of a sudden we have a tremendous amount of power because of the nonlinearity. So when we come back, we will continue in this trajectory. And I think we won't let out the assignment yet until Wednesday, but you have an assignment to implement a neural network. So you can start, you should read. I'm sorry?
What does the assignment do?
What does it do?
When?
Oh, always 6.5 days after it's out.